A car engine burns fuel to generate energy that drives the engine's pistons up and down. The crankshaft converts the linear piston movement into rotational motion, which causes the connected flywheel to rotate. Basically, a car engine's main function is to convert the chemical energy stored in fuel into the rotational motion of the flywheel. The force produced by this rotating flywheel is called torque, and it's this torque that ultimately turns the car's wheels. Car engines are incredibly powerful, providing the constant energy needed to propel vehicles at high speeds. However, engines have a significant limitation in that their torque range is limited. This limited torque range creates several problems for vehicles. The engine cannot move a car from a complete stop because the torque required for initial acceleration falls outside the engine's torque range. Similarly, when climbing hills, cars need substantially more power than the engine's torque range can normally provide. To solve this fundamental challenge, engineers developed the manual transmission, which is a sophisticated system composed of various gear combinations that can multiply the engine's torque when needed. It's called a manual transmission because the driver manually selects the appropriate gear combination based on driving conditions using the gear shifter. While a manual transmission may appear complex at first glance, understanding it becomes much simpler once you understand the basic principles of how gears work. Let's start by exploring these fundamental gear concepts. In any gear system, the gear connected to the power source through a shaft is called the driving gear, while the gear that receives power from the driving gear is called the driven gear. When the driving gear and driven gear mesh together, they rotate in opposite directions. To make them rotate in the same direction, engineers add a third gear between them, called an idler gear. This gear serves purely as a directional converter without affecting the overall gear ratio of the system. The relationship between gear sizes directly affects both speed and torque output in predictable ways. When driving and driven gears are the same size, both components have equal speed and equal torque output. When the driven gear is larger than the driving gear, torque increases while speed decreases proportionally. When the driven gear is smaller than the driving gear, torque decreases while speed increases proportionally. To understand this relationship clearly, imagine a large gear with 32 teeth meshing with a smaller gear having only 8 teeth. When you rotate the large gear once, the small gear completes 4 full rotations, spinning much faster than the large gear. This happens because the smaller gear has fewer teeth to travel the same circumferential distance. This relationship between gear size, speed, and torque can be represented by a simple mathematical formula known as gear ratio. You divide the number of teeth on the driven gear by the number of teeth on the driving gear to determine the ratio. In our example with 8 teeth divided by 32 teeth, we get a gear ratio of 1 to 4. This means the small gear spins 4 times faster than the large gear. But there's always a trade-off. While speed goes up by 4 times, the force goes down by 4 times. You're trading power for speed. Even though the small gear spins 4 times faster than the big gear, its torque gets reduced by 4 times. These basic gear ideas will help us understand how manual transmissions work inside. Now let's look inside a manual transmission to see exactly how it operates. A manual transmission consists of 3 main shafts that work together to transfer and modify power from the engine to the wheels. The input shaft connects to the engine through the clutch system, which can be disconnected by pressing the clutch pedal. The output shaft connects to the vehicle's wheels through the differential mechanism. The countershaft links the input and output shafts through various gear combinations. The input shaft has a gear at its end called the input gear, which constantly meshes with a corresponding gear on the countershaft. Since the input shaft gear and countershaft gear are identical in size, the countershaft maintains the same speed and torque as the input shaft. Additional gears of varying sizes are permanently attached to the countershaft at different positions. These gears continuously mesh with corresponding gears mounted on the output shaft. However, the output shaft gears aren't directly connected to the output shaft. Instead, they rotate freely around the output shaft. The output shaft has raised sections called splines. Synchronizer hubs fit over these spline sections, with synchronizer sleeves positioned above each hub. The hub's outer surface and the sleeve's inner surface have matching splines that interlock, ensuring that when the sleeve rotates, the hub rotates with it in perfect synchronization. A shift rod, controlled by the driver through the gear shifter, can slide each sleeve forward and backwards along its hub's spline section. Each output gear has additional teeth machined into its outer edge beyond the normal meshing teeth. When changing gears, the driver moves the gear shifter, which slides the appropriate sleeve along its hub to engage with the selected output gear's additional teeth. When the sleeve interlocks with the gear's additional teeth, both components begin rotating together as a single unit. Since the sleeve connects to the hub through splines, and the hub attaches to the output shaft spline section, this creates a direct mechanical connection between the output shaft and the selected output gear. Essentially, when a driver shifts gears, they're sliding sleeves on synchronizer hubs to establish different gear connections between the countershaft and output shaft. This selection process determines which gear ratio will be active for power transmission. While the additional teeth on output gears and sleeves are designed for easy interlocking, they can grind against each other due to different rotational speeds during gear changes. To prevent this mechanical grinding, engineers developed synchronizer rings positioned between output gears and hubs. The synchronizer ring lines the teeth of both the ring and gear, allowing the sleeve to slide smoothly onto the gear without harsh grinding noises or mechanical damage. The synchronization system is crucial for smooth gear changes and long transmission life. Before engaging first gear, the driver presses the clutch pedal to disconnect the input shaft from the engine. This disconnection reduces input shaft speed significantly, making gear changes smoother and easier to execute. Moving the gear shifter forward slides the appropriate sleeve backwards, connecting the output shaft with first gear and initiating vehicle movement. In first gear, the countershaft gear is considerably smaller than the corresponding output shaft gear, creating substantial torque multiplication. First gear normally has a gear ratio of 3.8 to 1, meaning it increases torque by 3.83 times compared to the engine input, while reducing rotational speed by the same ratio. This high torque multiplication is essential for moving the vehicle from a complete stop. Second gear engagement occurs when the driver moves the shifter to the second position, causing a sleeve to connect the second gear to the output shaft. Second gear normally has a gear ratio of approximately 2.06 to 1, providing less torque multiplication than first gear but allowing higher vehicle speeds. Third gear engagement follows the same mechanical process, with its sleeve connecting the third gear to the output shaft. Third gear normally maintains a gear ratio of approximately 1.4 to 1. Fourth gear represents a special case in most transmissions, with a gear ratio of exactly 1 to 1. This configuration is called direct drive because the engine speed and output shaft speed are identical, with no torque multiplication occurring. Fifth gear has a gear ratio of 0.8 to 1, which actually reduces torque while increasing speed beyond the engine's rotational speed. This configuration is called overdrive because the output shaft rotates faster than the input shaft, providing excellent fuel economy at highway cruising speeds. Reverse gear operates differently from all forward gears, requiring the vehicle to be completely stopped before engagement. In reverse gear, an idler gear is positioned between the countershaft and output shaft. When the driver selects reverse through the gear shifter, this idler gear moves into position and meshes with both shafts simultaneously, reversing the direction of rotation and causing the vehicle to move backwards. Since the vehicle must be stationary during reverse engagement, synchronizer rings aren't necessary for this gear selection. Manual transmissions demonstrate that seemingly complex mechanical systems become quite understandable when you grasp their fundamental principles. The entire system relies on basic gear relationships and the clever use of synchronizers to provide smooth operation across multiple gear ratios.